Okay, let me finish. Let me finish this lecture number 2, and I already know that I will skip a significant part of lecture number 3, and then I'll do some general remarks. So let's continue with the notion of stoichiometry. Given some reaction, then we have seen that there is a relation between the change in number of moles of species I and J in that reaction. And so similarly, you can write it in terms of the change in the mass of species I and J. All you have to do is just divide by the molecular weight. And so you can express that in terms of the mass fraction relation between two species I and J. So let's say that the global reaction is fuel plus oxidizer, and I use nu sub F and nu sub O for the stoichiometric coefficient of the fuel and oxidizer, and no need of prime and double prime because they don't appear in the product. And so that last relation can be written as simply the change in YF divided by nu F WF is related to a similar change for the oxidizer. And if I integrate from the initial state or unburned state, say U, denoted by U, up to a certain state, where the mass fraction is YF and YO, then this integration lead to this relation. And if at the end of the process there is no fuel and oxidizer, in other words, there is complete combustion, then of course YF is 0, YO is 0, and that ratio between fuel and oxidizer, or between the similar nu O molecular weight W and so on, and I denoted by nu, this is the stoichiometric ratio. In fact, usually it's written as fuel divided by oxidizer, but in my notation here is nu is the oxidizer divided by the fuel. And we define the equivalence ratio if in a given mixture the initial amount of fuel and oxidizer is YF and YO, unburned, relative to the stoichiometric value. This is usually referred to as the equivalence ratio. So if you are less than stoichiometry, you have a lean system or a lean in fuel. And if it's above 1, it's rich in fuel. So we have an explicit expression in terms of the simplified system that we discussed. Phi equal to 1 is stoichiometry, below and above 1 is lean and rich. We can also talk briefly about the adiabatic flame temperature, which is defined that in a given combustible mixture, if you approach chemical equilibrium by means of an isobaric system, in other words, constant pressure, then and adiabatic, then the temperature which is attained is the adiabatic flame temperature, and I denoted with T sub A, A for adiabatic. So for an adiabatic isobaric process, the change in enthalpy is equal to 0. There is no change in enthalpy. In other words, H unburned and equal to H burned. And that's for the mixture. So if you write for all the species, it's going to be the sum of YI, HI, similarly for unburned and burned. And if instead of the enthalpy, you use the enthalpy of formation plus the integral of Cp dt, which is often referred to as the sensitive enthalpy, then you get the following relation. And if I reorganize it by moving the enthalpy of formation terms together, you get that the difference here between YIU minus YIB times the enthalpy of formation is the difference between the integral of Cp burned minus Cp unburned, integrated from some reference temperature up to the burn temperature, okay, TB. Now, if and the CPU and the CPB are specific heat of the mixture, not of any specific. Now, if for a one-step global reaction, then again, as I mentioned before, the J is F, and nu J prime is nu F, and the double prime is 0 for the J, but there are other species, say, then the relation that we derived before can be rewritten here, where I just use the integration. Well, I use essentially that relation integrated from the unburned to the burned state. And if we essentially, well, I have to go back to the previous one I derived, sorry, which I derived here. So if I use this relation, then, which is written actually just here, then we can identify that the left term is essentially, well, you can verify that later. It's essentially the heat of combustion, okay? So the difference between the integral of Cp from the reference to the burn state of Cp burn minus the same integral Cp unburned is essentially the heat of combustion, with the coefficient just appearing due to this relation. Now, if the reference enthalpy is chosen as the unburned temperature, and the final temperature is a adiabatic flame temperature under isobaric condition, which is what we derived before, then essentially what you get is that this YFB is 0. The coefficient here is taken to the other side of the equation. CPU is integrated from TU to TU, so it's 0. So the only integral that you have is the Cp burn from TU to TA. And this is essentially an implicit relation for the adiabatic flame temperature. In practice, what it is often written in terms of, I don't know if I wrote it below, yeah. In practice is often written in terms, well, no. What I wrote below is that the same relation, what we have done here, we've assumed, maybe I skipped saying that, we assumed that the fuel was totally consumed, and that's why YFB was set equal to 0. If you do the same thing and you assume that complete combustion of oxidizer, you get a similar relation, but you know, for the complete combustion of oxidizer. Now, let me see if I put that in or not. Yeah, here it is. So I put here a summary of the two. But what I wanted to point out is this. Usually in practice, one uses, instead of the Cp per unit mass, using per mole, the molar Cp. And then that whole term is just the integral of the molar Cp dt is Q. And the way that you compute the molar Cp of the burned gas depend on the number of moles and the CPI of the different species. And so since TA appear in the numerator, in the upper part of the integral here, you cannot integrate that unless you know what TA is. So basically what one uses iteration. In other words, you assume a certain value of TA, you compute the left-hand side. If it's equal to Q, great. If not, you improve your TA until it is agreed. So this is typically how it's done. The reason I wrote those here, it's because for analytical purpose, it's important to see that there is an analytical formula for this. And since, sorry, in all the discussion that we will have later on, the Cp will be assumed constant, then we can actually integrate this relation. by pulling out the integral. And so what you get is actually a simple expression for the adiabatic flame temperature. Remember that this is good under the assumption that it was derived. So we have an expression for the lean, an expression for the rich. The difference is here. And of course, these two expressions are equal to each other when phi is equal to 1, because, as you remember, YFU divided by nu FWF is exactly equal to YOU. That's exactly stoichiometry condition. So we have the two expressions, and in principle, the expression is such that the adiabatic flame temperature reach about maximum near the near stoichiometry, and it's lower on the two end. Yeah, I mean, that comes simply because this quantity, YFU divided by this, is the maximum at stoichiometry. Okay. And here is some experimental data that show this. Okay, for me, it was just important to write this in order to see that we have, for simple system or simple models, we have an analytical expression. What is missing here in this formula is the fact that in the product there is always dissociation, and that changes really the expression. Usually it lowers as a result of that the adiabatic temperature. So this is a higher end value, but it's not, in reality it's usually lower, a little lower than what you obtain here. I think I mentioned that somewhere here. Yeah, I mentioned it here. Product dissociation lowers the value of TA. One must then need to incorporate some atom conservation to determine exactly what are the final product, and then you can determine the adiabatic flame temperature. Okay, so this forms the end of this lecture, and I will move to the next one, but I am not going to discuss the first part, which is the deflagration, detonation, differences, and so on. Maybe I will just say in few words. I want to avoid it, but I'll say in few words what the idea is there, and you can look at it up. So the idea is, if you have a one-dimensional system and you have a combustion behavior that is going on in some section here, where all the important things happen, namely heat conduction, species diffusion, chemical reaction, and so on. The question that one asks is in this one, and if you know the state of the gas far on one end, the question is there a solution or a wave that this reaction propagate to the left? And if it does, then we want to know what is the velocity of that wave, what is the wave velocity, the propagation velocity, V0. And the second question is, okay, what's going to be the end product when this wave travel as a whole, right? And so those are the two major questions. So what you do, you write a one-dimensional equation, and you integrate them from one end to another. And when you do this, you can relate the conditions on the far upstream, P0, ρ0, T0, Y0, everything that you have. The gas is at rest far upstream. The wave is moving into a quiescent mixture, fresh mixture of reactant. And the condition on the right are going to be the products, the ρ infinity, P infinity, T infinity, and so on. So just integration of the equation from one end to the other give you that relation. But unfortunately, this does not give you the speed that it propagates, okay? The discussion that I'm going to skip is to show that there are, when you have heat release, in other words, when what is happening here also release all this process, release heat, there are two possible solutions that you would get for the propagation speed V naught, and therefore for, of course, the product. One is a relatively slow velocity, and one is a very fast velocity, and that's the difference between the two. The deflagration are the slow process, or the flame, and the detonation are the fast one. And we can identify certain properties, but we cannot determine from the simple analysis the speed itself, except in one special case, which is known as the Chapman-Jouguet condition, but that's not general. One more thing one should say, that it's not enough to know that there may be such a state, even if I knew the velocity, because mathematically you should be able to obtain the connection between the two, or the structure, as we say, of the wave that connects the solution on one end to another. In other words, it's not enough to get this algebraic relation. You have to show that the differential equation that connects one end to another exists, and it satisfies the conservation equation. So there are two questions here. Usually that one address is to determine the propagation speed, and second, to make sure that indeed a solution exists. You see, if you had any little elaborate course in differential equation, you will know that if you have, say, an equation that have two equilibrium, the idea is to find a trajectory that connects one equilibrium to another. But it's not guaranteed that if you start from one, you will always meet the other. It depends on the nature of the solution near the equilibrium point. Usually that's what is referred to as different singular point, if it's a source, if it's a sink, if it's a saddle point, and so on. So generally speaking, the idea is the same that you have to show. Anyway, I'm not going to discuss all this. We will focus on the rest of the week on deflagration, which is weak or subsonic velocities. In particular, the structure that will be interested is a flame, and therefore V naught is going to be the flame speed or the laminar flame speed, as it's referred to. So this is what I'm skipping. And now I'm going to go back to the equations. Well, here are the comments I was going to say, but anyway, boom, boom, boom. That's it. So now we're going back to the equation, and this is really important because this is the summary of what I want to use the rest of the week, okay? Maybe before I summarize this, I will say a few words. I mean, I didn't expect from you, after listening to me talking relatively fast, to derive or rederive what I presented to you before. And I didn't also expect that all of you will fully see all the details that I have, shown. But I am sure that you get some ideas. That first of all, the equations are very complicated and complex. And there are all kinds of assumptions made in dealing with this equation. For example, the multi-component diffusion law that I showed you is not often used, and often used more in numerics, say, you will use the Stefan-Maxwell relation. Or you will use simpler things like the effective diffusivity, or you use the model that I want to use, which is a dilute mixture. So you see, I wanted you to understand that there are such assumptions made when you deal with such problem. I just show one example, but there's similarly the heat flux relation. You will find a lot of reference in the literature that do not account, for example, for the diffusion heat flux term, which was the, if you remember, yi, vi, hi in my equation, or something like this. So it's important to be aware of this because sometimes the results that you get depend on what you put in. And so if you know that you have assumed something, which is fine, but you have to know the consequence. And that's really what I wanted to bring in. And now I will more or less follow the same way in the rest of this lecture, because I will be using some of these simplification this week. So here is the model essentially that we will be considering. It's a 1-2 reactant mixture in general. Sometimes we even use a 1 reactant mixture. 1 reactant doesn't mean that there's only 1 reactant. It means that the other one is a big quantity and we don't pay attention to it, or we focus only on one which is in small quantity. In other words, the deficient one. Okay, because when the deficient one is consumed, the reaction stops. So that's the important one. So, and in that sense, the reaction rate will be written as such. We allow for reaction order NF and NO, not necessarily equal to 1, although very often we simplify them to be 1. Because we are interested in understanding the qualitative nature of the system and not so much the little detail that maybe are not affecting much, unless you prove somehow in one of your future work that changing the reaction order is very significant in some system, which is perfectly fine. So that is important to know. Okay, the second thing is we are going to assume that the CP are all the same and equal to CP, and we furthermore, we will assume that it's constant as well as the molecular weight is constant. Where does the molecular weight constant appear? It appears here. Remember, there is Yi divided by Wi, which is the mixture molecular weight. If I assume it's constant, I'm not taking into effect the fact that there are variations due to the concentration or mass fraction, okay? So we're going to use this with W as a constant. The fact that Cp is a constant will be used here. Well, it's already used here from the previous derivation, but the lambda, mu, and rho di also are going to be assumed constant, because then in this term, the lambda be pulled out, and you get the Laplacian of t. Here, the rho di is taken out, and you get Laplacian of yi. And so those are assumptions that we are going to make. And also in the momentum equation, mu is a constant, and that whole term, which include even the compressibility term, simplified to this form, which is the Laplacian of the velocity and 1/3 the gradient of divergence v. Okay? So these are the simplifications that result from that assumption. It is useful to get a sense what non-dimensional equation you get. It's very useful certainly in theoretical studies to write equation dimensionless form. Some people argue that in numerical computation it may be good to use dimensional form. But remember, dimensional form are good only for one specific mixture, one specific condition, one specific data, and so on. Anyway, this is what we will do to write equation dimensionless form. So we have to choose a reference, and that's not unique. So when you read a paper, be careful. Only recently I saw a review of an article where they argue that this is not the same as paper number 2. But they didn't pay attention that paper number 2 defined the parameter the reverse than paper number 1. So be careful that these coefficient parameters are systematic or consistent. We are going to use now the following characteristic value: the state of the fresh mixture, P naught, rho naught, T naught, as the units for P, rho, and T. Then we're going to choose a characteristic speed. At the moment, we don't know what it is. So at some point, we will determine it. We cannot proceed with an analysis, get results without knowing what is the reference value you chose. But we can leave it unspecified for some time. So we're going to use V naught. And then the diffusion length, which is the thermal diffusivity divided by V naught. Remember, thermal diffusivity is centimeters squared per second, divided centimeter per second, you get a length. So that's the diffusion length. The thermal diffusivity is lambda over rho Cp, and that's going to be the length that we use. But by the way, I can use slightly different length. I can use, instead of the thermal diffusivity, the fuel mass diffusivity of the oxidizer mass diffusivity, and the equation are going to be a little different, right? But that's a choice we made here. The diffusion time, then, since I have a length and a velocity, I have a diffusion time. Okay. If we do this, here I said that the choice is not unique. For example, the heat release divided by Cp has units of temperature. And you can choose that as your reference number. The difference will be that if I choose my first choice, T initially is 1, because T naught is the reference temperature. And the final temperature is going to be, let's say, the adiabatic temperature, whatever the temperature will come. If I choose the Q over Cp, then 1 is going to be usually the burn value, and 0.1 or something like this will be the unburned value. So you see the difference. In some example, I may use this, but I will let you know. I can also use different lengths, not only the diffusion lengths, for example, and we are going to see some examples like this as we go along. Okay. In the next, so in principle, to do that, you write, for example, the dimension velocity is going to be the velocity divided by V naught, similarly with all the terms. And typically, so the tilde will be the dimensional value, and then you drop the tilde to avoid having too many notation confusion. Okay, so here are the equations that you get. So there's nothing changed about the continuity equation. If you put the dimensionless quantity, the same on the first term, same on the second term, so you get that equation. In the second equation, which is the momentum equation, you're going to get a coefficient in front of the gradient pressure, 1 over gamma m squared. Gamma is the ratio of specific heat you used before. M squared turned out to be V naught divided by the square root of gamma P naught rho naught. And so that's essentially the ratio of the velocity to the speed of sound. And this is defined as the Mach number. So that term appears here as a Mach number square. Then in front of the viscous term, you get the Prandtl number, which is defined as mu Cp over lambda, which is essentially the viscous diffusivity divided by the thermal diffusivity. And some of you familiar with fluid mechanics will remember that usually you get here the inverse of the Reynolds number. Well, since we chose the length to be the diffusion length, then the inverse of the Prandtl number is indeed the Reynolds number, or the inverse of the Reynolds number is the Prandtl number, okay? So there is no inconsistency here. Okay, the next, in front of the gravity term, if you keep it, there will be a coefficient which is often known as the Froude number in the fluid mechanics literature. Essentially is the inertia relative to the gravity, okay? So this is the ratio. All dimensionless quantity are ratio of things. Of course, you can multiply, divide by something and call it ratio of another similar quantity, but it's the same thing. Then in the species equation, you're going to have coefficients which are known as the Lewis number. Remember that we scaled the length with the thermal diffusivity. And in this equation, there is mass diffusivity, though the ratio should appear somewhere. and so it appears as Lewis number. So the Lewis number is the ratio of the thermal to mass diffusivity, and in the way that we write them here, they would appear as the inverse of Lewis number fuel, Lewis number oxidizer. Just as an interesting comment, if you come from chemistry or chemical engineering end, you may see that the Lewis number is defined as the inverse of that, the reverse, as the mass diffusivity divided. Most combustion literature use this notation. So you have to be, again, careful. That's the comment I was making earlier. So here they are defined. Then in the reaction rate, if you choose that the fuel is 1 mole of fuel and so on, or if you divide by nu FWF, then you will have the ratio nu in the oxidizer here. That's why I refer to nu as oxidizer versus the fuel, because of its appearance in this equation. Okay, in the next equation, which is the energy equation, what you have, you're going to have here a term gamma minus 1 over gamma, which is, again, the ratio of specific heat. And the viscous term is multiplied by Prandtl number and the Mach number squared. You will see the importance of this in a minute. It makes sense that in a combustion system, viscous friction or heat produced by viscous friction is minimal compared to the heat of combustion, and typically it's going to be neglected, but you will see how systematically this is done. The next term here is the little q, which is the heat release parameter, which will be the heat release divided by the entropy of the fresh mixture, CPT naught. The equation of state is take a simple form, which is almost obvious, and then the reaction rate will depend on the mass fraction of the fuel, the oxidizer, if you want, nu F, nu O, remember that the mass of low action tells you that it's the law of mass action. I don't know if I said that before correctly. Is the rate depend on the concentration. Okay, concentration is rho y divided by W. And so that's where this rho appears. So it's rho to the n, which will be twice from NF plus NO. And then there will be a coefficient here, D, which even though it will look a little complicated, is rather simple. It's LD over V naught, which is exactly the flow time that we defined before, the time scale. What's on the bottom is can be seen as, in fact, it's simple. If you see a reaction of order 1, it's essentially the reaction time. It's roughly I say roughly because there's all this molecular weight that come in, but it's essentially it's like the rate constant, and the rate constant is it's a time, or the inverse of the time that of the reaction time. Well, anyway, so this is often known as a Damkohler number, and it's the flow time divided by the reaction time. Okay. So now we have all the coefficient, we have all the equation dimensionless, and an important discussion is actually come from this part of the equations, okay, the momentum equation. In combustion, which I rewrote on top, I rewrote here. Usually the propagation speed is relative of flames. We said we are not talking about detonation anymore. Is relatively low. It's relatively slow. It may be a meter per second at the most under some circumstances. So it's much smaller than the speed of sound in air. So the Mach number is very small. And if the Mach number is very small, much smaller than 1, then what you see is that, well, you can see 1 over, so that's very big. Or if you like, multiply the equation by m squared. This is small, this is small. Grad P is almost 0. So grad P is 0 means that the pressure does not depend on the x, y, z coordinate, on the spatial coordinate, but it may still depend on time. And so in general, I would write it that P is some function of time, and I use a capital P. But I still have to conserve momentum. It's not enough to say grad P is 0. And so I have to take the next term, which must be proportional to Mach number squared. So I called it P hat. So when you substitute that in here, you'll get the momentum equation, which is written here. Now, in one-dimensional system, you usually don't need to compute the momentum because you can determine the velocity from the mass conservation. But when you do multi-dimensional system, you have to satisfy momentum. And so you have to account for these small pressures, which I called here. And the equation is well balanced because the flame propagates slowly, so the momentum is small. And it's balanced by small pressure, okay? P, the little p. So this is this equation. Now, that also plays a role in the energy equation because you see in the energy equation, I missed it. Next one. There is a Mach number here, right? And so viscous heating, as I already alluded to before, is negligible, it's small, so it's going to go to 0. But also the PdT will change because it will involve the capital P plus a Mach number squared term. So the only thing that is left in this equation is the capital P, which is, if you like, the mean pressure in the combustion system or in the volume. Okay, so this is 2 of the simplification of this low Mach number approximation. There's a third one, and the third one is the equation of state reduced to rho T equal to just P of T. Now, in many systems, like in when the flame is freely propagating, the pressure does not change in time. It's constant, it's ambient pressure. And so in that case, this P is 1, this dP is 0, and you have to then solve this equation. So, okay? So actually, I think I wrote it next. So if first I summarized here the low Mach number equation. Okay, they are known as such in the literature. And then, which is, I emphasize here in yellow, the main changes from before. I eliminated the hat here with the understanding that that's the additional or the small variation in pressure from the mean pressure P. And let's see what I wrote next. Yeah. So in the absence of any external pressure fluctuation that may cause P to change in time, or the mean pressure P in time, P is equal to 1. This is gone, this is 1, this is as is. It's the pressure that you need to calculate. Rho T equal to 1 means that the density and temperature are essentially the inverse of each other in that approximation, which is approximately correct in combustion. Now, when there are situations where, I mean, look, I had one pressure in the equation. I numbered the number of equations, number of unknowns, and it was the same. But now I have 2 pressures, and I don't have more equations. So how do I obtain an equation for this capital P when it is important? Well, if it's from external fluctuation of the pressure, it's known from the boundary condition. But if you have, for example, combustion in a closed vessel, then it's not known. The pressure gets built up, and you have to compute it. So the way to obtain it is essentially by integrating the energy and continuity equation throughout the whole volume. So when you do that and you have an integration of the whole volume, this is what you get, where the divergence theorem here is used to rewrite this term in terms of the flux from the surface S of the volume. Note that rho t is P, so it can be pulled outside, which is here, and then you have divergence V, which gives you this. Same thing, this term comes from the Laplacian here, and then the integral of the reaction rate. Now, if you're in a closed volume, the normal velocity to the wall is 0. There's no penetration or no slip boundary condition, if you like. And if it's under adiabatic condition, this term is 0. There is no heat flux from the wall. And then what you end up with a simple equation, dp dt, in dimensionless form. It's written as such. In other words, it's related, the pressure buildup is related to the integral of the reaction rate, okay, throughout the whole vessel. I will do at least one example in the next few days of combustion in a closed vessel, so I will remind you this relation again. And the last comment, or two of the last comment, is one of them is the so-called coupling functions. So what you note from the equation of the species and the temperature, that apart from the Lewis number, which appear here, the equation on the left-hand side of the equation is very similar. It's almost the same operator when Lewis number is 1, right? So when Lewis number is 1, the operator is d by dt, rho d by dt minus Laplacian. So, but the right-hand side is a little different. But you can always multiply one of the equation by a factor to eliminate the right-hand side. So for example, remember this is 1. If I multiply this one by nu and subtract one from the other, I eliminate the right-hand side. Or if I add the yf to t and the yo to t after multiplying the y equation with q, I eliminate the right-hand side. So anyway, this combination, t plus qyf or t plus qyo divided by nu, are satisfying equations that the right-hand side is 0, namely reaction-free equation. In other words, these quantities are not produced or destroyed during combustion. They are just conserved. And so sometimes they are called conserved scalars, or I like better coupling functions, but this is only true for unity Lewis number. By the way, there are only 2 out of the 3 equations which are reaction-free or conserved. It's either t plus qyf or t plus qyo, or the difference between those two, which can be obtained simply by the difference between those two. So only 2 are. The third one still have the full reaction term in it, the full complication that need to be solved, even for unity Lewis number, okay? An exception will be the fusion flame in certain limits, but we will talk about that. So it is a great simplification to use unity Lewis number, but as we will see later, it's also a problem because there's a question of instabilities, question of small changes in Lewis number create some effects that sometimes need to be taken into account, and so it's not a good approximation always. Okay, and the last slide of today is the so-called constant density approximation. Now, just on the face of it, if I say constant density, you are right to tell me, well, it has nothing to do with combustion. In combustion, there is chemical reaction, there is heat release, and as a consequence, the density changes significantly. But I first want to point out to you some mathematical fact, and then the rest I will briefly tell you what it is. So if the reason those are all the equations that we need to solve. I wrote everything apart from the equation of state. And I put that in a red box and this one in a blue box because they seem to be independent of each other unless rho varies, right? So when rho varies, of course, due to combustion, the temperature rises. It changes the density. The density changes the velocity field. And the two are coupled. But if you assume some average density, then the two systems are not coupled. So, of course, it's a great mathematical simplification. Now, as I said, starting that it's not a very convincing, or it's not a good approximation in combustion. Nevertheless, there have been certain things related primarily to the diffusion of species into each other, or sometimes what have been referred to, did I write it here? Yeah, thermodiffusive effect or thermodiffusive model that can be learned for such a system despite its simplification. And so I will rarely use it in this week, but I may have one or two places where I will mention something about it. So anyway, you may face that term or this in your future studies or in the literature. When you see constant density, that's what's referred to. Sometimes it's hidden behind the word thermodiffusive, but it has the same meaning. By the way, some of you, since you have all had some combustion before, you must have heard of Burke-Schumann approximation, which I will discuss. In fact, Burke-Schumann used the constant density approximation without explicitly saying that. So it has been useful. So anyway, those are the different... I knew I wanted to say something. It's very important to be careful that when you use the constant density approximation, essentially you're saying rho is equal to 1. So you cannot also use the equation of state. So you have to abandon the equation of state. In other words, when you do some simplification, you have to be consistent. It cannot be just blindly done. I think the next slide say end. Oh, this says something else. Oh, it says that there was a formal, derivation of that system under the assumption that the heat release is not 0, but it's small. And it makes sense. Small heat release give you small temperature, small changes in density. And so when you put it in the velocity field, it's approximately a constant to leading order. Does say end. I will see you tomorrow. It was great to have your attention. Thank you.